Hi all, today we will discuss about an important topic called instruction set architecture. All of you know about instruction sets, what is meant by instruction. So first I'll give you a brief introduction about what is meant by an instruction. So an instruction is basically a unit of execution in a program. So if you develop a program in any programming language such as C, C++, Java, Python or any other language, the basic element of execution is an instruction. So when you execute an instruction, I hope you know how to execute an instruction. So instruction execution contains four stages and they are referred as fetch. The first stage is fetch. Second stage is decode, and third stage is execute, and the last stage is store. So these are the four stages of instruction execution. So let me describe in detail about these four stages. The first stage is fetch. All of you know that once a developer writes a program in memory, that program will go and store in secondary memory. When a user or developer or a programmer develops or writes a program, it will go and store in secondary memory or hard disk. And from that, those instructions of the program has to be transferred into main memory. So if a program want to be executed in a memory, it has to be present in the main memory. If you want to execute a program, it has to be in main memory. Next, from main memory, the processor fetches instruction one by one. So it is the responsibility of when I say processor, all of you know that processor is a combination of control unit, ALU, registers, and cache. So a processor is a combination of ALU, that is arithmetic and logical unit. Second one is control unit and some special purpose register, and there exists an internal cache. So these all together referred as processor. So a processor, what do you understand when I say a processor fetches an instruction? I'll explain you in detail about this fetch because it is the most important one. Let's take an example. Add a comma b. So this is a simple instruction stored in the main memory, and all of you know that the CPU is divided into two parts. The first part contains ALU, second part contains the control unit. The ALU part is called data processing unit, and this is called control unit. This control unit has some special purpose registers. Similarly, ALU also contains some kind of registers. First, we'll try to understand the registers that control unit holds. The first important one is IR register. IR stands for instruction register, and next register is PC. PC stands for program counter. The IR register should store the instruction that is being currently executed by the processor or ALU. So remember, IR stands for instruction register, and it is a special type of register which is used to store the current instruction that is being executed by the processor. Next comes PC. PC stands for program counter. The program counter is also another type of register which contains the address of next instruction to be executed. Let's assume 100 is the address of the current instruction that is being executed by the processor, and the next instruction is 101. So this PC stores 101. The PC should contain the address of the next instruction, that is 101. When a PC contains 101, next it has to fetch the instruction which has an address 101 that is stored in the main memory. So for that we use two special registers related to memory. One is MAR and other is MDR. So what happens when the processor wants to, or control unit wants to fetch an instruction whose address is in the PC, the PC has the content of the PC has to be transferred to MAR. So the content of the PC has to be transferred to MAR. 101 will be transferred to MAR, and this MAR is sent to main memory. The main memory takes this 101. This main memory takes 101. Now this is my memory, and it has an address add a comma b, which has address 101. Now this is my MAR MDR, memory address register and memory data register. So now what should happen? The PC is a program counter which stores 101 address. This has to be loaded into MAR. MAR stands for memory address register. So this memory address register, if you keep an address in the memory address register, the system bus address, this MAR address is placed on address line of the system bus, which goes to main memory and searches the memory for the address 101. And the moment it finds the instruction, this add 101 add a comma b is placed in memory data register, which is transferred to IR instruction. Now finally what happens? The IR registers contains IR register gets the instruction add a comma b. Now the PC is incremented. So what happens? PC points to now 102 address. So this is address of next instruction to be executed. Now this is the currently executed by instruction. This is the current instruction. So once the processor or control unit gets this instruction, all of you know that instruction contains two parts. One is opcode and other is, if this is my IR, this IR contains two parts: instruction opcode and operands. So this is called opcode, this is called opcode, these are called operands. This is called opcode, this is called operands. So what happens? These operands plays an important role. First, the control unit gets this opcode and it decodes. This is called second stage of the instruction execution. Remember, the first stage was till the instruction transferred from main memory to IR is called fetch. This is called fetch stage. This is called fetching of an instruction. After fetching an instruction, the control unit has to take the opcode part of the instruction and it has to decode. After decoding, it will send a signal to ALU. Now ALU has to execute. If ALU want to execute, it needs operands. Third stage is now the control unit sends that a decode signal, a decode signal, that is called add decode signal. So let's take an example: add, subtraction, multiplication, division. Add is 0 0, subtraction is 0 1, this is 1 0, this is 1 1. So 0 0 0 1 1 0 1 1. 0 add is 0 0. This is the control signal. So if CU sends 0 0 to the ALU, ALU understands it is an add. If it sends 0 1, subtraction. If it sends 1 0, multiplication. If it sends 1 1, it is called division operation. So like that, ALU understands that it has to perform a any arithmetic operation. It has to perform any one of the arithmetic operation. This is called decoding. Now the ALU understands that it has to perform any arithmetic operation. Now it is the job of ALU. ALU receives 0 0 from control unit. So with this it understands that it has to perform an addition operation. But to perform addition operation, ALU needs operands. So these operands again are stored in main memory. So when they are stored in main memory, you need to perform another fetch, but this type we are fetching operand. So fetching operands. Operands may get stored in the register, in the main memory, or within the instruction itself. Remember, this is called addressing modes, which we already discussed. Next, once ALU gets an operand, it stores in a special registers, one accumulator and BR. You know, accumulator is an important type of register. AC stands for accumulator. Accumulator is another type of or special type of register. AC stands for accumulator. And what is the specialty of the accumulator means? The result, if you say add A comma B, the instruction is, if the instruction is add A comma B, and let's assume A is B, B is equals to 20, AC register contains, let's assume 10, BR register contain 20. When ALU performs addition 10 plus 20, the results 30 is again stored in AC. So this is the specialty of the accumulator register. So the accumulator is one type of register where the results are stored by default. So this is a brief introduction about instruction, instruction execution, instruction format, what are the stages of instruction execution. Now we see an important concept called instruction set architecture. You know about instruction. An instruction set means a group of instructions Then what is this mean by what do you mean by architecture? Architecture is with respect to parallel processing. How to write instruction for vector processor or array processor, or how to write instructions for the pipelining processor. All those things we'll discuss in instruction set architecture. So let's take an example of instruction architecture. This is the blocks of a microprocessor that all of you know, and it is these are called program execution section. This program execution section contains literal address operation, program memory. So what is this program memory means? This program memory means literal address operation program memory. Remember, this is a program memory, and this is called program counter. You know, the program counter contains the address of next instruction to be executed, and this is called IR, stands for instruction register. See, the PC has a communication with stack. This is important. We should try to understand why PC is communicated to stack. Because very frequently, if you are executing an instruction, if the processor gets disturbed, then what happens? The address of the PC has to be stored somewhere else just to handle interrupt. Remember, we discussed a lot thing about in previous video. We discussed about an interrupt previous class. So interrupt is a some kind of disturbance to the processor. So interrupt is nothing but some kind of disturbance to the processor. So when an interrupt occurs, what processor has to do? It has to complete the current instruction execution, and it has to store the address of next instruction. Where is the address of next instruction is stored? Of course, program counter. So program counter is a register which contains the address of next instruction. So when a processor receives an interrupt signal and the processor sends an acknowledgement signal, acknowledgement that I have received the interrupt, the next moment processor continues the current instruction execution, because the current instruction cannot be stopped. Execution of the current instruction can't be stopped because it might be in the middle of any stage. It might be in the fetch stage, it might be in the decode stage, or it might be in the execute stage, or it might be in the store stage. So the processor might be executing an instruction which is in any one of these stages. Those stages can't be stopped. So what has to do? It has to finish the current instruction execution once it receives interrupt. After that, the processor sends interrupt acknowledgement signal saying that I received the processor, and after that it has to do some household things such as, see, the program counter contains the address of next instruction, the address of next instruction. So the program counter has to, the content of the program counter, in case of interrupt I am discussing what is the case, when the we are discussing the case where program counter interacts with stack. So the program counter interacts with the stack when the program counter interacts with the stack. That is, uh, in this situation, interrupt occurs after finishing the current instruction execution. The processor has to store the content of the program counter. Remember, program counter contains address of next instruction. Let's assume the address of next instruction is 102. This has to be, this 102 has to be stored in the stack. This has to be stored in the stack. So this is the case where the processor interacts with the program counter interacts with the stack. So you know the property of the stack. Stack follows first in, last out, or last in, first out. This is called LIFO, LIFO, or FILO. First in, last out, or last in, first out. This is called a stack. Next, we discuss about instruction decoder. Instruction decoder, what it does, it receives an instruction, that is add a comma b, from the processor. When it receives the add part is decoded by this instruction decoder. What happens here, the instruction decodes the instruction, that is add a comma b. Add part is decoded by instruction decoder. Remember, these are the timing, control, and register selection. So they will receive clock signal, reset, and some interrupts. So this is part. As of now, we have seen that processor receives an interrupt, but which part of the processor receives an interrupt means this is the part, that is timing, control, and register selection. So it is the unit which receives some timing signal, which sends the timing signal to program counter, instruction decoder, and it receives the timing signal from a literal address operation, clock, and it will send timing signal to ALU, control signal to ALU. So this is called control unit. So with this functionality, you should understand that it is nothing but a control unit. So the control unit is the one which sends timing signal and control signal and register selection. It also performs register selection. Which register has to be selected for which phase. Let's take an example. Here, this timing control unit is sending signal to a unit called flag and special function registers. So this function register gets an input from ALU. It sells some internal bus, and you know this is an accumulator, this is an ALU. ALU stands for arithmetic and logical unit. It is the responsibility for performing arithmetic operation. So this is called block of a microprocessor. It is majorly divided into two parts. The first part is program execution section, and second one is register processing section. First one is called register. First one is called program execution section and second one is called register processing section. Now remember, this one register processing section contains what it contains. It contains accumulator, RAM and data registers. Accumulator, you know, right? It's a special type of register. RAM and data register. These are the I/O interfaces that receive signal. I/O controllers. So these are the I/O controllers. Processor. Remember, processor should have some way of communicating with I/O interfaces. So these are called I/O controllers, which resides on the motherboard or a microprocessor within microprocessor. So these are the I/O units that resides within the microprocessor, and this is RAM and data registers, and they use some internal bus. Internal bus is nothing but some physical wires hardwired on the motherboard. You might have seen some blue color lines. They are nothing but the internal bus. Flag and special function registers. Flag and special function registers uh, receives the control signal, timing signal, and register selection from control unit. So this is block of a microprocessor. It's really necessary to understand this. The program execution section, register process section. So remember, this is called program execution section, and this is called register processing section. This is called register processing. This is called program execution section. So the program execution section contains, I'll repeat once again, it contains stack, which follows the principle of last in first out or first in last out. And the most important part here is, see, the program execution section and register processing, both are handled by the timing control register section, which is nothing but the control unit, which is called control unit. So the control unit is the one which makes these two blocks to be communicated in a microprocessor. So the register process section contains ALU, arithmetic and logical unit. It contains ALU, that is nothing but arithmetic and logical unit. It contains an accumulator, RAM and data registers, I/O devices, flag and special function registers. What is meant by a flag? See, flag is a bit which is set to either 0 or 1. Let's take carry flag. While performing arithmetic operations, you might understood that the flag register might be set to 0 or 1. 0 means there is no carry flag, there is no carry has been generated while performing arithmetic operation, and when it is 1 means yes, carry has been generated over here. So this is the real meaning of the carry flag. Next we have instruction set architecture. So when I have instruction set architecture, this is called software and this is called hardware. They both are competing. So instruction set has to communicate with both hardware and software. So instruction set means it just not only communicates with the software, it has to balance, it has to communicate both software and hardware. So let's try to understand the part of computer architecture related to programming. So the part of computer architecture related to programming. So our goal is to discuss instruction set architecture. Remember, our topic is instruction set architecture. There are a hell lot of things to be discussed here. The part of the computer architecture related to the programming. So when I say instruction set architecture, the computer architecture means hardware of a computer is related to programming. Includes native data types. So what is meant by native data type? That I'll discuss. I'll take an example of native data type. Let's take an example of some instruction set which is getting executed on hardware. Let's take, this is my hardware and this is called instruction set. So this instruction set. So the instruction set, we are discussing about a point called what is meant by a native data type. So the native data type means if this is my instruction set which interacts with hardware, let's try to understand with some example. Let's take your instruction set contains integer a is equals to 10. It is one instruction. Now this has to be anyway executed with the support of hardware. How? If I have a hardware means the registers, control unit, ALU, the length of the registers. So here most important part is the length of the register. Let's assume register contains 32-bit. So this hardware has 32-bit registers. So when you declare int a is equals to 10, your hardware thinks that an integer has to be stored. One integer can be stored in a one register. That means an integer is getting 4 bytes. Remember 32 bits means 4 bytes. So this is the default data type that hardware knows, which is called native data type. So native data type, here integer is called a native data type. Why it is called as a native data type? Because when you declare a type of integer, the hardware understands that it has to allocate 32 bits of memory for storing an integer value. So what happens here? So what's happening here means the processor, when you declare an integer variable int a is equals to 10, the hardware understands that integer has to be allocated 4 bytes of memory, and the length of the register is also 32 bits, that is 4 bytes, and the main memory also, the length of the main memory might also be 4 bytes, that is 32 bits. So the length of the memory word is 32 bit, the length of the register is 32 bit, and the integer takes 32 bits. Integer requires 32 bits of memory or 4 bytes of memory. This is called native data type. And it is very important to understand, have an idea what is meant by a native data type. I hope you are getting. I'm just explaining with an example. Now we'll try to understand what is its actual meaning when it comes to native data type. So signed integer types, native data types example, not only integer, there are so many things. Native data type means it can be, now we'll see an example for a native data type. So the example of native data types is like character, which is called char, integer, int, and integer. When I say integer, it is by default unsigned integer. So if you want to specify, you can specify it as signed integer or short integer or long integer, or there is also another data type byte, floating point number. So I'll explain example of native data type. Character, int, byte, float. These are called character, int, byte, float. These are called native data types. And in general, character takes 1 byte, and it comes to integer, there are so many types: signed, unsigned. This is called unsigned. Signed, short, long, like that. And byte is also takes 1 byte. Float, we have float and double. So this is about native data types in computer architecture. So this has got an important role. Everybody should understand what is meant by native data type. So now we discuss what we are trying to say. Include native data types, instructions. So what is meant by an instruction? You know about this. Registers. So include native data types, instructions, registers, addressing modes. See, registers means they can be program counter register, IR register, or MAR register, or MDR register, or stack pointer register, accumulator register, BR register. Apart from this, there are some general purpose registers like R1, R2, R3. These are the different possible registers. Next, we have addressing mode. Addressing mode means where the operand is present. In simple way, what is the address of the operand? Simple. You can easily understand the address of the operand means sometimes what happens, the instruction might be present within the instruction itself. This is called immediate mode. Sometimes the address might be present in the register. Sometimes the address of an instruction might be present in the register, or sometimes the operand value is itself present in the register. Sometimes the address of a instruction which is stored in the memory location might be present in the register. Sometimes the instruction itself might contain the address of the instruction stored in the memory. So these are the different possibilities. These are called addressing modes. So we have to include native data types, infrastructure, registers, addressing modes, memory architecture, interrupt. I need not to explain about interrupt because interrupt is a some kind of disturbance to the processor. So interrupt means some kind of disturbance to the processor. It is some kind of disturbance to the processor. Interrupt means having some kind of disturbance to the creating some kind of disturbance to the processor. Next is exception handling. What is meant, you should understand what is meant by an exception and error. Remember, exception is something that can be handled. It is also one type of error, but exception is a kind of error that can be handled during runtime or during execution of a program, or sometimes what happens. So interrupt is nothing but some kind of disturbance to the processor that we have known. What is meant by an exception? So first you should understand the difference between exception and error. Exception means something that can be handled by your program during runtime. Next example is, if you are performing a division A by B, and if you during execution it is encountered that the value of B is equals to 0, then A by B is a divide by 0 exception that you can test, that you can handle basically. Similarly, if you are trying to if you are trying to open a file which doesn't exist, file not found exception. So like that, there are so many exceptions that can be handled during runtime. But when it comes to error you can't handle, like hardware failure, power failure, memory crash, hard disk crash that your program cannot handle. It has to be handled by OS. If OS gets crash, it is also called error. If your OS can't boot, it is an error. So you can the main difference between exception and error is that exception can be handled and error cannot be handled. Next we have external IO, that is R1 R2 to PCR registers, move, add, include, add instructions. ISA, instruction set architecture, specifies set of opcodes, machine language and native commands implemented by a particular processor. This is important. Particular processor, if you a processor, example for a processor is AMD and Athlon or Intel processor. These are the two famous processors, Intel or AMD. So the AMD, if it is a processor is an AMD, it can be it has its own instruction set architecture. If it's an Intel, it has its own.